Before a single transistor is etched, before a photon of extreme ultraviolet light touches anything, every chip on Earth begins as a cylinder of crystallized silicon pulled slowly from a molten bath in Japan. Two companies largely decide whether that cylinder exists at all. The question this map answers is direct. If that crystal pulling node gets closed, does China have a line already routed around it? Or does the entire downstream web stall at the very first step, before the headline machinery even becomes relevant? A choke point is not a factory or a firm. It is a junction in a dependency web where every downstream line converges and no alternate route yet exists. A breakthrough is what happens when someone lays a new line around that junction. The web reshapes. The choke point either dissolves or retreats further toward the source. This map traces that shape from the finished chip backward, one node at a time, to find where the web is still forced through a single gate. The object at the center of this trace is one 300mm silicon wafer, a mirror-flat disk about the diameter of a dinner plate, weighing roughly 100 grams, grown from a crystal ingot over several days in a controlled furnace. It carries no transistors yet, no circuits, no logic. It is simply a surface, and everything else in modern semiconductor manufacturing is written onto that surface by machines that cost hundreds of millions of dollars and processes that take months. The wafer is where the chain begins. The map starts here. Trace the line backward from a finished chip, and the first physical thing you arrive at is this disk. Whatever the chip does later, wherever it was designed, whichever foundry processed it, the wafer underneath is the origin. But calling it a commodity input misreads what it is. The surface must be flat to within a few nanometers across the full 300 millimeters. The crystal must be nearly defect-free. The purity of the silicon itself must be extreme in a way that does not map easily onto everyday intuitions about clean materials. Impurity concentrations for prime-grade wafers are measured in parts per trillion. That is not a figure of speech. A single stray atom of a contaminant at a density above a few parts per trillion in the wrong layer can alter the electrical behavior of the structures being built on top of it. Think of the global supply chain as a river system, where every tributary eventually flows into two main channels before reaching the delta. You can describe the delta's complexity all you want: the distributaries, the sediment management, the engineering. But if those two main channels narrow, everything downstream runs dry first, regardless of how sophisticated the delta has become. Shin-Etsu Chemical and Sumco, both Japanese, together account for a large majority of global 300mm silicon wafer supply by area shipped. The exact figure varies by source and year, but industry observers and analysts consistently place the two firms at well over half of global output, with the remainder divided among a small number of others, including SK Siltron in South Korea and Siltronic in Germany. No Chinese supplier appears in the tier that supplies leading-edge fabs at confirmed prime-grade volume. This concentration is not a recent market maneuver. It reflects decades of accumulated process refinement, of running crystal-pulling furnaces through millions of production cycles, logging yield data, adjusting pulling speeds and thermal gradients, and building up the kind of institutional process knowledge that does not transfer through a specification sheet. Here is a take I will put on record directly. The wafer node is underweighted in most Western coverage of the semiconductor supply chain. The conversation jumps to extreme ultraviolet lithography machines, to photoresist chemistry, to design software, all of which are genuine choke points. But the wafer sits further upstream than all of them. You cannot have a lithography problem if you never had a wafer. My read is that the wafer choke point is the one that would trigger earliest in a supply disruption, before the headline machinery even becomes relevant to the calculation. Node. the 300mm silicon wafer. Status: a junction China still routes through a single foreign gate, specifically through Japanese supply, with no confirmed domestic bypass at prime grade and leading-edge volume. Follow the wafer one step further back along the material line, and you arrive at the crystal ingot. It was cut from, and behind that, the polysilicon feedstock. The ingot was grown from. The Czochralski process, which is how nearly all monocrystalline silicon for semiconductors is made, works by dipping a seed crystal into a bath of molten silicon and pulling it upward very slowly while rotating it. The process concept is not secret. What determines whether the resulting crystal is usable at advanced nodes is the purity of the polysilicon going into the melt and the control of the thermal environment during the pull. Ultra-high purity polysilicon, what the industry calls electronic grade, is a distinct materials node from the lower purity solar grade polysilicon that feeds photovoltaic panels. The same element, vastly different specifications, different suppliers, different economics. A glassblower can work with ordinary sand melted down, and the result can be beautiful and functional. But an optical lens for a precision measurement instrument requires silica processed to a purity order where even trace contaminants change the optical outcome. The furnace concept is the same. The feedstock requirement is not. And treating them as the same problem leads to misreading who actually controls the upstream node. Electronic-grade polysilicon production has historically been concentrated among a small number of suppliers, including Wacker Chemie in Germany and Tokuyama in Japan. China has built significant polysilicon capacity, but the bulk of that capacity is solar-grade. Reports suggest that Chinese electronic-grade polysilicon capacity exists and is expanding, but independent confirmation that it meets the purity specifications required for leading-edge wafer production at volume is limited in the public record. The distinction between solar-grade and electronic-grade purity is not a minor technical footnote. It is roughly the difference between water clean enough to drink and water pure enough to be used in the rinse stages of semiconductor fabrication. Both are called clean water. They are not the same problem. Node: electronic-grade polysilicon and crystal pulling purity. Status: a junction where a domestic line is under construction. China has capacity and growing output, but the line is not yet confirmed at the purity grade that leading-edge wafer production requires at volume. Step back now and read the concentration as a network property rather than a market share statistic. The question is not only who makes the wafers, but what it would take to reroute the line and how many layers of the downstream web would freeze during a reroute. The 300mm wafer node sits at the base of a stack. Every lithography step, every deposition step, every etch step, all the capital equipment that processes a wafer over the course of several months operates on a surface that Shin-Etsu and Sumco largely define. China's leading-edge fab ambitions, concentrated at domestic foundries working toward more advanced nodes, are themselves dependent on wafer supply that currently runs through this junction. Chinese domestic wafer producers, including firms that reporting identifies as Xing Semiconductor and National Silicon Industry Group, have been scaling 300mm capacity with substantial state support. Volume is rising. But volume rising and prime grade confirmed are two different readings of the same ramp, and conflating them is how the map gets misread. Leading-edge fabs evaluate incoming wafers on defect density, surface roughness, and crystal perfection metrics that are tested rigorously before the wafer is accepted for production. No independent benchmark has publicly confirmed that Chinese domestic 300mm wafers have cleared the bar a leading-edge node requires. What is confirmed is that Chinese domestic wafers are used in production, at mature nodes, where the specification tolerance is wider and the defect budget is more forgiving. This is where I want to push back on my own earlier framing, because the standard argument that wafer making is lower technology than extreme ultraviolet lithography and therefore more easily copied deserves scrutiny. That framing is misleading. The difficulty is not in understanding the physics of the Czochralski process. The physics are published and taught. The difficulty is in achieving and sustaining the defect density and purity consistency that a leading-edge fab demands across millions of wafers at production volume. Those are manufacturing process secrets in the deepest sense. Not equations, but procedures, accumulated yield data, furnace-specific calibration histories, and the judgments of engineers who have run the same process for years and know which readings to trust when the instrument says one thing and the crystal says another. The gap between being able to pull a 300 mm crystal and being able to supply prime-grade wafers to a frontier fab at scale is not a knowledge gap. It is an accumulated process learning gap. Those are different problems with different timelines, and the second one does not respond to investment the same way the first one does. Consider a bridge that handles local traffic reliably. The engineering that qualified that bridge for its current load is real engineering. But qualifying the same structure for fully loaded freight at highway speed requires a different set of tests, different tolerances, a different confirmation process. The bridge exists. The question on the map is whether it carries the specific load the route requires, not whether it carries any load at all. Node: Chinese domestic 300 mm wafer supply at prime grade. Status: a junction where the bypass line is under active construction and carrying some traffic. Confirmed at the grade and volume the mature node portion of the network needs, but not yet confirmed at the grade the frontier portion requires. Follow the line now into the policy dimension, because a choke point is only as significant as the conditions under which it closes. Japan has historically been a stable supplier of silicon wafers, and there is no current export restriction on silicon wafers comparable to the controls placed on semiconductor equipment. But the web does not care only about current policy. It cares about structural exposure, about where the lines run and how many of them pass through a single junction. The concentration of 300 mm prime-grade supply in 2 Japanese firms means that a shift in export policy, whether voluntary, negotiated, or coerced by circumstances, would propagate downstream faster than any other single materials control in the chip supply web, because it would affect every fab, every node, every geography simultaneously. Extreme ultraviolet machines affect only fabs running the most advanced lithography. Wafers affect everyone. Japan aligned with the United States and the Netherlands in 2023 on semiconductor equipment export controls, covering certain deposition and lithography tools. Silicon wafers were not in that package. Industry observers have noted that wafer supply was conspicuously absent from the controlled item lists, and the reasons for that absence are debated, whether commercial interdependence, diplomatic calibration, or a judgment that the downstream disruption would be too broad and too fast to manage. The structural exposure exists regardless of whether the lever is pulled. The concentration is the fact, and the policy optionality follows from it. A junction box in an electrical grid can sit quietly for years with every route running through it normally. The fact that it has not failed and has not been isolated does not change its position in the network diagram. It is still the single point where multiple lines converge. The map shows the junction. The decision about whether to throw the switch is a different question, and the answer to that question is not in the wiring. Node: policy optionality over the wafer supply junction. Status: a node that has not been gated yet. The choke point exists structurally. The switch has not been thrown, and China's exposure here is present and unhedged at the prime grade level. Now, to the one node where no bypass yet runs. Prime grade 300 mm silicon wafers at leading edge volume. The specific combination of grade and throughput required by a frontier node fab running the most advanced lithography processes available. This is where the map shows a dead end, and it deserves slower treatment than the segments before it. The case that this is a durable dead end is this. The gap between what Chinese domestic producers supply today and what a leading-edge fab requires is not the kind of gap that closes because engineers read the right papers or run the right simulations. Shin-Etsu and Sumco have been refining crystal pulling and wafer polishing for leading-edge nodes across decades of high-volume production. The process knowledge is partly documented, but a significant portion is embedded in the operational practices of experienced engineers who have watched specific furnaces respond to specific adjustments over years, in the yield records of facilities that have been running at this standard through multiple generations of node transitions. Reports suggest that Chinese domestic producers have skilled engineering teams and are improving across measurable dimensions. There is no confirmed independent evidence that the defect density and surface specification requirements of a frontier node production line have been met at the volume a leading-edge fab requires. The case that a bypass is being constructed and could close the gap. Chinese state investment in domestic wafer capacity is substantial and has been sustained. The trajectory of improvement in Chinese semiconductor materials has, in several adjacent nodes, been faster than external analysts initially projected. Solar-grade polysilicon, where China is now a dominant global supplier, was once similarly concentrated in foreign hands. That ramp took years and it happened at scale. Electronic-grade purity is a harder target, but the direction of investment is clear, and reports suggest that trials at more demanding specifications are underway. The timeline is genuinely uncertain. The direction is not. My synthesis call on this stated plainly. China's wafer ramp is real and the volume trajectory is upward. But volume and grade are not the same variable. The domestic wafer story so far is primarily a story about mid-grade supply for mature nodes, not a confirmed story about prime-grade supply for leading-edge production. The map shows a bypass being constructed, and it shows real progress. But that bypass currently terminates one grade short of the choke point it needs to clear, and the remaining distance is measured in manufacturing process learning time, which does not compress easily and does not respond to capital in the way that building a new factory does. The dead end is real at the current moment and at the leading-edge grade. It is not permanent in the sense of being physically impossible to route around. It is durable in the sense that the remaining distance is measured in something that investment alone cannot simply purchase. Read the map now as a complete picture. Some nodes China has already routed around. Mature node 300 mm wafer supply. Chinese domestic producers are confirmed at volume for this grade. The bypass is operational. Solar-grade polysilicon. China dominates global supply. This node is already domestically controlled. A range of general semiconductor materials at mid-specification, deposition chemicals, gases, packaging materials, has seen Chinese domestic supply expand significantly over recent years. The nodes that remain unrouted at the grade that matters. Prime grade 300 mm wafers at leading edge volume, where no confirmed bypass exists. Electronic grade polysilicon at the purity ceiling for leading edge wafers, where domestic capacity is growing but top grade confirmation is pending. And the policy optionality held by Japanese suppliers, which represents a structural lever that exists in the wiring of the network, whether or not it is ever activated. My plain read of this web. The wafer node is more exposed than the mainstream conversation about semiconductor supply chains acknowledges. The conversation lands on extreme ultraviolet machines and photoresist chemistry because those are dramatic and visible and involve some of the most sophisticated engineering on Earth. The wafer is quieter. It sits further toward the source, which makes it easier to omit from the analysis and harder to replace quickly if the junction closes. The most consequential vulnerabilities in a dependency network are often the ones that feel solved because nobody is currently talking about them. That 300mm wafer, the flat disk that ran through this entire trace, is the object the whole downstream web rests on. Not the extreme ultraviolet machine, not the photoresist, not the design software, the blank surface. And right now, the blank surface at the grade the frontier requires still largely comes from 2 Japanese companies before anyone else touches it. The most consequential choke point in the semiconductor supply web is sometimes the one nobody drew on the diagram because it was so far toward the source that everyone assumed it was already solved. Which node closes next? Does the domestic wafer ramp confirm prime-grade supply before export controls reach the wafer layer, or does the policy lever move first? Drop your read in the comments. And if this kind of dependency map tracing is the analysis you want more of, the subscribe button is right there, and turning on notifications means you get the next trace when it goes up.